Today I will talk about local limits and proportional attachment graphs. When Pim invited me, he wanted me to talk a little bit about the opinion dynamics. So I figured I would start by giving a bit of an introduction about why is it that I'm interested in local limits in the context of that other problem. And in some other occasion, I would be more than happy to share what are the opinion dynamic models are themselves. So this is mostly going to be a talk that is joint work with Cheyenne Banerjee, who's our second speaker today, and our joint student, Pravanka Deka. So to get started, let me start by saying that I'm going to be talking most of the session on marked directed graphs. So even if I'm not specifically saying that the graphs will be directed, I often think of problems that require the direction to be an important component of what we're modeling. So we have a graph G with a vertex set V, edges E, and what you might see as something new is here attributes. These attributes come from a different set of places depending on the model, but they can also encode information that is specific to the problems that we're analyzing. Things that are specific to each vertex, to each individual. If you're thinking about graphs that represent people, then the behavior of people can be encoded into these marks. So they can also be called latent variables in some cases because they modulate how different vertices connect to each other. And I'm just going to assume in general for the purpose of this talk that the marks take values in some separable metric space S. Throughout the talk, di minus is going to be the in degree of a vertex I, and di plus is going to be the out degree of vertex I, and the in degree being the number of neighbors, inbound neighbors, and out degree the number of outbound neighbors. And as I said, I want to explain a little bit why I'm interested in local limits. In reality, the bigger picture question that I've always been interested in is analyzing processes that are functioning on top of a graph. My interest many years ago started with the analysis of the PageRank algorithm, Google's PageRank, and centrality measures in general. And I will show you a little bit more about that later today, but PageRank is a recursion on a graph. So there's nothing inherently random of the PageRank recursion once you have the realized graph, but it's still something that fits into a bigger context, as I will explain today. As Pim mentioned, I've been, as of the last few years, very interested in modeling opinion dynamics on complex networks. And in these kind of models, some of them will fit into the structure of the problems that I'm going to explain right now, where the most important thing is to understand the local behavior or the local structure of the underlying graphs. These type of context of the processes that I'm usually interested in also include some nice problems on financial cascade modeling and even production networks in economics. So there's many different things that fit into this framework, which again will bring us down to why I'm interested in local limits. So in general, the general framework of many of these problems, including the PageRank and the opinions model, these are recursions of this following form. You have a value of a process in time, here my time is k, on a vertex I, where we're using as function or map phi, that is mapping the information about the vertex itself, potentially also itself, Ri. I'm missing here on Ri. Okay, I'll add that later. And information about the attributes of the neighbors, information about the values of the neighbors, and potentially some random noises that are changing the behavior of the process. In the case of PageRank, there's no noises. This is, as I said, a deterministic map once you have a graph. But in the case of the opinion models of many different types, usually this is a random process. It's a Markov chain on the graph, where the interactions are occurring among the different individuals on the graph. So something of this form in general. Here, G is usually a deterministic function depending on the problem that we're analyzing. And because this function requires information not only about the vertex latent variable, but also about the in degree and out degree, I encode that usually as some vertex mark xi, which is why we're interested in understanding that later. So as I said, my typical examples include Google's PageRank, but also the opinion dynamic models like the DeGroot, Johnson, Fritkin model, or the noisy voter model. All of these fit into this kind of situation. So
Mariana,
why locality?
There's a question in the chat.
Can I, let me see. Can you?
So this is math
Yeah,
cal
the question is,
I can also ask it
Master-
by audio. Yeah, I don't understand the relation between the mark set A, calligraphic A, and S. Like S being a property of the node is a possible type of calligraphic A.
so here, when I said that the vertices have some marks, some vertex marks or latent variables, I will talk about a lot of them in a minute, but think of these as the weights on an inhomogeneous random graph. So the level of extrovertedness that vertices have, and that makes them attach more likely to highly extroverted vertices and not so than more introverted ones, things like that. But in the case of PageRank, in the vertex mark, we usually also use a teleportation parameter, which tells us how likely you are to jump to different places when you reset your exploration or your walk. Things like that will get encoded into the attribute mark. So because depends a lot on what the model we're looking at, what they are, I usually just assume that S is some general space. Doesn't matter what it is. It's usually a polished space to make sure that all the math works nicely. But other than that, it can affect the construction of the graph, but it can also be external to the graph. Does that explain a little more what those are?
Yeah, maybe it's gonna be clear during the talk, but thank you.
Okay. So here, again, those latent variables usually stay there if they're needed for whatever reason. But we also incorporate those which may or may not be direct functions of the attributes. Okay, so why locality? So let me try to explain a little bit. Think about any of these processes, let's say a Markov chain or a Markov process Rk, as time goes by, as k goes to infinity. Most of the examples that I was mentioning, we're interested in a situation where there is a stationary behavior. So as time goes to infinity, this process converges to something, to some vector valued process that tells us how likely you are to, let's say, have an opinion of a certain type of things like that. Now, the interesting case that all of the examples that I have in mind include are for when the map phi defines a strict contraction. And this is a very important observation to make. Once the map phi defines a strict contraction under some suitable metric, then the convergence rate of the process is geometrically fast. But once it's geometrically fast, that means that we can easily approximate the stationary behavior with a finite number of iterations of the process. The moment we do this, which is something that numerically we would do without thinking too much about what's going on, that moment tells us that all we really need is the local information about the vertex. Why? Because these are directed graphs. So if I only need 7 iterations, I only get to see the influence of my neighbors that are at most a distance 7 from me. And the moment that happens, the entire problem becomes local. Means that the value of my process at time k is a function only of the k neighbors, or the neighbors at distance k of vertex I for each of those. And that is what triggers my interest in local weak limits. Why? Because the moment that you have this situation, which occurs in many interesting problems, then all we need to know is, can we say something interesting about the local neighborhoods in the graph G to be able to describe the stationary behavior of the process R? Now, I noticed that there was another question on the chat. So do you want to ask your question? Something about the noises, I believe. No?
Yeah, I just wanted to ask,
Can you speak a little bit louder, please?
So why is there a subscript? One of the noise depends on the vertex and the other depends on the
Yes.
edge.
So these are noises on the vertices right here, and these are noises on the edges.
Hello?
Does that explain it? So these kind of recursions can have both kinds of noises, usually one at a time. Let me see the chat again. Yeah, so the reason why there's two
Hello,
vertices
can you
is
hear
because
me?
of that. Yeah, I sort of can. So in this piece, there's two indices because these are noises on the edge J to I. And these, on the other hand, are noises only on the vertices. So depending on the model, we've seen both. Yeah? Does that answer your question?
I think it's
Okay.
it's okay. Yeah.
So now that I tried to make a little introduction of why local weak limits are interesting or important to understand, let me start going into, what is it that we can normally say about graphs? So the way that we think about it, like the big network that we're studying, if it's opinion dynamics, usually this is a social network that consists of people talking to each other and sharing their opinions on a variety of political topics, for example. So this graph is very large, and interesting enough, because it's so large, the specific nature of the graph doesn't matter as much as the statistics of the graph. So we might as well think not of the specific graph that we have in front of us, but as that graph as a realization of a random graph model. And if we take this approach of modeling the problem, then we're going to pick some random graph model, usually a sequence of graphs in this by the number of vertices. As the number of vertices grows, and we consider that sequence and try to understand what its local behavior is, right? Now, for most of the models that you may have heard of, what you're going to see is that they have a very interesting local behavior. They're all tree-like. And what does it mean to be tree-like? Well, I'm going to take a directed exploration of a typical vertex. So I pick a uniformly chosen vertex at the top, and I'm going to look at the directed exploration. I'm going to see all the neighbors that are coming in at distance 1. Right? And then I'm going to go and see all the neighbors at distance 2 and so forth. Once we get to each of these neighbors, I also explore how many outbound neighbors they have, but I don't explore those. I only keep the exploration in the direction in which we're doing it. So in this picture right here, what we're looking at is the exploration of the in component of my vertex right here, IN, right? So once we do this, on most of the models you may have heard of, what's going to happen is that this is a typical picture that you're going to see. It's going to look like a tree. It's going to take a long while before you encounter the first cycle, right? The first connection of a vertex that you hadn't seen before, and that you had already seen before. And because of this, up to the point where this happens, the local neighborhood, this, is essentially a tree. And this is actually something very, very typical of most models. Just to give you an idea of how typical this is, let me mention some of those models. There's basically two classes of models, the static ones and the dynamic ones. Static models are meant to represent like a snapshot, a picture of your graph at that instant, whereas the dynamic models tend to attempt to explain how the graph is formed. So in a static type of model, iteration gn and gn plus 1 may or may not have much in common, whereas in the dynamic 1 and n plus 1 will definitely be very much related to each other. Now, among the most famous static models, you have the Ardos-Renyi, the Trung-Lu, the Norris-Raytu, the generalized random graph, the configuration model, the stochastic block model. All of these models are static, and all of them are going to be tree-like. And among the dynamic models, probably the most famous one is the Albert-Barabasi preferential attachment model, and there's many generalizations that have come out after that. Now, this talk is going to focus exactly in one of those generalizations, one that Sharon and I have studied in the last couple of years. Any questions so far? Okay, so before I go deeper into what exactly it means to look like a tree, let me explain what look like a tree means. In order for me to say precisely what look like a tree is meant to be, let me just give you a definition of what a graph isomorphism is. So many of these models, the configuration model and the model I'm going to talk about today, are not actual simple graphs, they're multigraphs. So this is my definition of multigraph isomorphism, where we have the vertex sets are here VE and VE prime for the other graph. And what we're counting is there's a bijection that I'm going to call sigma between the vertex set of one graph and the vertex set of the second graph, and the number of self-loops is the same on both, and the number of multiple edges is also the same. So as long as we have this, we're going to call G and G prime to be isomorphic to each other. Because of the models that we tend to consider, we also define this probability measure, which is taking into account the latent variables. So again, back to these models right here. Any of these have latent variables that are needed to generate those models. In the case of the first, so these ones, with the exception of the configuration model, all of these fall into a family called homogeneous random graphs or G graphs. And in that case, the latent variables are some sort of parameters that we usually refer to as weights that are controlling how likely any two vertices are to connect to each other. These are usually called, I like to think of them as the extroverted parameters. So two nodes that are very extroverted or have a higher chance of connecting than two vertices that are very introverted. In the stochastic block model, those latent variables include community belonging, so labels. You're either conservative or liberal, for example, in the opinion model case, or you can be a bot, in which case you have a very different behavior. So these kind of information goes into the latent variables. In the configuration model, the latent variables include the given, the prescribed degree, in degree, and out degree upfront. So because of those get encoded into these probability measure, and that's the one that we use for analyzing the models going forward. Now, before I give you the standard definition of local weak convergence, let me talk about what a strong coupling is. So in the talk today, and most of the things that I have done related to random graphs over my career, I like to think about the actual coupling between the local weak limit, the shape of the object of that tree that I showed you, and the graph explorations of all the vertices in the graph simultaneously. So we say that a strong coupling holds for the family Gn if for any two uniformly chosen vertices independent of each other from the graph, we can find two IID copies of the limiting object such that the two explorations up to depth of level K are isomorphic to each other with high probability. And if we have marks, that the marks are close to each other uniformly at distance epsilon. This is for any K, usually for a K that grows with N as well, right? Now, in the special case where the marks are not continuous, then we can actually take the marked isomorphism and we take epsilon equal to 0. But there are many interesting examples where the marks themselves are not discrete. So that's why we have this sort of more generic formulation. Now, this definition also extends not to just two explorations, but to countably many. But these are, minor things that are really sort of straightforward. So once we have that, that means that we have the standard definition of local weak convergence in probability, which says if I have any particular graph G fixed and any set of marks, then if I take the average, the proportion of vertices whose incomponents of depth K look exactly like G with the marks that I'm given, then that converges to some law over here that is given in terms of the limiting object, right? In this case, a tree. Now, all these definitions do not require that my limiting object to be a tree, but just because in this talk everything is a tree, I'll just leave it that way. And here, this is sort of the standard definition of local weak convergence in probability with the corresponding marks. So now let me go to just to the actual model that we're going to be talking about today and mention quickly that for all the static models that I mentioned before, the local weak limit is always a Galton-Watson. In the case of the stochastic block model, it's a multi-type Galton-Watson with as many types as the number of communities. But the more general case of the, let's say, degree corrected stochastic block model, which falls into the family of inhomogeneous random graphs, then you end up with potentially an infinite type Galton-Watson process. And the directed case is something that Sharon Prabank and I recently worked on, and hopefully that'll be out in the next few days. So among the dynamic models, the Albert-Barabasi model is a continuous time branching process that is stopped at the random time. And so is a directed version of it. And one model that I want to mention just to give you an example of something that doesn't fit into the context of what I'm going to be talking about today is the directed preferential attachment model with reciprocity, where every vertex has a chance of connecting in either both directions or in the opposite direction at which the time they arrive. This kind of model is actually very interesting, but it's one of those examples that doesn't fit into any of the things that I'm going to be talking about. So now to the model that I wanted to share with you today. This is what we're going to call the collapse branching process. And that will fit into the local tree-like behavior, and it will have nice properties. It's quite versatile, as I will show you. Before I start with the model, any questions on the prelims? Nope. Okay, great. So what is a collapse branching process? We're gonna start by defining some general attachment function F. This is a non-negative function on the integers, whatever you might want it to be. Then we're gonna use a continuous time branching process, and we're gonna call psi. That is driven by the pure birth process psi F, which basically is just your pure birth Markov chain that is being modulated by the attachment function F. On top of that, we're going to add a sequence of ID random variables, integer random variables that we're going to call the DI pluses. The notation is to suggest what they will be. They will become the out degrees of the graph themselves. And as you can see, because these are generally chosen, the model is going to have the ability to replicate any out degree distribution as you see fit. Once we have that, we're going to define the corresponding random walk that goes associated with those DI pluses. And we're going to associate families of vertices according to the sizes of those DI pluses. So I'm going to call VI. V1 would be the first family, which will consist of the members 1 through D1 plus. Family 2, V2 would correspond to the members from D1 plus 1 all the way to D2 plus D1 plus and so forth. So here's the exact number. And the interpretation of what these families are, or these sets VI are, imagine that you have families of individuals, of people. Each family has a random size given by the DI plus, and they all come essentially together. And they will show up together. And as they show up to the graph, they will start attaching to existing vertices in the graph. The graph that we're going to be analyzing is one that is obtained by collapsing the branching process psi according to the family sizes given by the DI pluses. So in order to create the graph, what we would do is we would run the branching process. This is a tree by definition, all the way until some random time at which we have accumulated exactly Sn nodes. Those Sn are going to give rise to n vertices once we group them according to the family sizes. Then each family gets collapsed into a single vertex I in our final graph, and we're going to preserve all the edges and self loops in the process of doing so, right? So what we're going to obtain at the end is going to be a multigraph that has exactly n vertices, and where the out degree of vertex I is going to be the family size DI plus. One thing about this model that I particularly don't like too much is that it has no directed cycles. This is the one feature that directed preferential attachment with reciprocity can do that, that would be important to use in reality. Here's a picture of how the graph gets built. So imagine that this is my continuous time branching process psi right here. In this picture, I'm not drawing them according to the time at which they arrive. They're drawn according to the distance from the root. So the root is vertex number 1. The next vertex to arrive was 2. Then vertex 3 came in here. Then vertex 4 attached to 2. So that's why it's being depicted in the 3rd level. Vertex 5 came here and attached to 4. You can think of those as a family that has children, and the children will tend to attach to their parents. So before I go forward with this, there's a question in the chat saying, can we do this with undirected graphs? Yes, you can collapse any process, and if you want, that's fine. So anyways, let me get back to this model. So now we have the timestamps, and their color, what they represent is the size of the degree. So in this particular example, I have the out degree sample. The first family is of size 2. The second one is of size 3. The third one has 1, 4, 2, and 3. So you can see the red family has 2. The green family has 3. The blue family has only 1 here. The purple family has 4. So here, 1, 2, 3, and 4, and so forth. So this picture over here, because it's a continuous time branching process, it's just a tree. However, once we collapse it, then it gives rise to this more interesting graph. Here we have node 1, because 2 attached to 1, that's the self loop. As I said, the children who attach only to their parents. Think of it that way. And this is vertex number 2, who also has a child that attached to itself. That's this edge right here. And then the other edges we preserve. At the beginning, you can see that there's going to be a fair number of multiple edges for the older vertices, which is typical in this kind of models. And as we go farther down, then this behavior of multiple edges and self loops is going to start decreasing, right? Which is what's going to lead to the behavior that I'll explain in a moment. Any questions so far on how the collapsing procedure works? No? So again, the main idea is that this is a non-trivial graph. It's interesting. It has cycles, it has self loops, it has degrees, out degrees that are completely random according to whatever prescribed distribution you like because of the way that we built it. So that's the nice feature that this model has. Now, some special cases that you may already be familiar with are the preferential attachment graph, linear preferential attachment, and the uniform attachment graph. So there's 2 special cases where I can pick f to be a linear function. If a is non-zero, then this is the preferential attachment Olvera-Cravioto type of graph. If a is 0, this corresponds to the uniform attachment graph. In general, we're going to refer to the case f as the general attachment graph. Now, the 2 models, the one that I just described in terms of the collapsing procedure and the one that is using an attachment graph do not coincide in general, with the exception of the linear function f. When f is linear, the model that I described in terms of the families that come together and get pushed into a single vertex is equivalent mathematically to the graph where each vertex comes in with a certain number of outbound edges, let's say di plus. So node I comes in, has exactly di plus outbound edges, and sequentially attaches those di plus edges to existing nodes on the graph according to this preferential rule, which is a ratio of the value of f of the existing vertices divided by the total weight of all the vertices present in the graph at that time. So these 2 cases coincide. The general f when f is not linear do not coincide, but they have similar dynamics. And that's just because if f is not linear, then, we don't have linearity. So, and we don't have, we can't exchange the 2 procedures entirely. Now, these particular models have usually been studied in the case where the out degree is fixed. It's a number m. So one of the things that this model does is that it extends that construction to as many out degrees and random out degrees as you wish under minimal conditions. So now let's go and do that exploration of this graph. So when we explore the in component of depth k of vertex I in this graph that we obtained by the collapsing procedure, you think like, hey, this is never going to look like a tree, right? I showed you the pictures. Just to remind you, here are the pictures. This doesn't look like a tree. This definitely doesn't look like a tree. As a matter of fact, this picture is never going to even get close to looking like a tree once we write it down. There's too many self loops and too many multiple edges between the same two vertices. However, what's happening in this kind of models is when we take a uniformly chosen vertex from the graph, we're not going to be sampling with high probability the old vertices. We're going to actually be sampling the younger ones. What Shannon will talk about later today as the fringe of the tree of the continuous time branching process. So when that happens, there's actually quite, you know, as I will show you, the typical picture is indeed a tree again, believe it or not. So here's how the expression goes. We're gonna choose one vertex, uniformly chosen at random. Here I'm gonna just call this for any vertex I to be the in component of depth k. And then we're gonna start exploring the in component. So only directed edges that are pointing towards it. As we go along, we're gonna keep track of the out degree that that vertex has. And we're gonna add that as a mark in our exploration. Now, if you have more marks for whatever the reasons you want, like what other problem later comes in, you can add those as well, if that is important to the model. And once we have this graph, then what this notation refers to is just I'm including the marks as the information of the in component of the vertex I. Now, in order to get a strong coupling in the sense that I defined it earlier, then I need to impose some conditions on what the attachment function f needs to satisfy. To start, we're going to assume that the out degrees actually have positive finite mean. Here, there's a little plus missing. So they have to have finite mean. That's a very, very minimal requirement for this purpose of this. And then we're going to have to assume that the function f is such that if this is the Laplace transform of my of the pure birth process, then it has to satisfy sort of minimal conditions in order for us to get regularity. So one of them would be the existence of a root to the equation, the Laplace transform equal to 1. So the Malthusian parameter lambda needs to be well defined. We need to assume that f is not growing faster than a linear function. Right? It cannot go faster than a line. We also need to ensure that it doesn't die entirely on the other end. So it needs to have a minimum value that is some kind of constant, strictly positive constant that is the minimal amount of attachment you can have. Otherwise, you end up with nodes that stop growing at some point. And then we need just a tiny bit more moments to the right of the Malthusian parameter. You know, that's really what this condition is. This is our technical conditions, but these have to do with that momentary function. So now let me describe what the limit of the graph is. So it turns out that we can construct the local weak limit of this graph by superimposing IID copies of the pure birth process and running the branching process associated to that. So if I have, and remember, we have a sequence here of the marks. These are going to be the sizes of the family. We're going to take a copies, DK copies of the pure birth process there and superimpose them. So now I get this aggregate point process that is giving me a random number of them together. So this is no longer, you know, Markovian, and it's no longer, you know, as pretty as the original once you start superimposing more than one. And once we have the superimposed process, we're going to create a tree run by that, a continuous time branching process driven by these new type of process with the associated marks DK. So it's again a tree with the marks. And what the theorem says is that if I take tau to be an exponential random variable with parameter equal to the Malthusian parameter lambda, then this tree, the CS here for reinforcing the fact that it is the collapsed tree, like the tree obtained for the local weak limit of the collapsed graph, then that converges in the local weak sense. The original problem, the collapsed graph, converges in the local weak sense to this collapsed tree right here. And in particular, it admits a strong coupling in the sense of the definition I gave you earlier today. So we can have finitely many explorations of uniformly independent chosen vertices, and each of those will be independent copies of our local weak limit. Now, you might wonder, why is this stopped? This is the first thing that I want to point out relative to the static models. In the static models, all the local weak limits are infinite Galton-Watson trees, or potentially infinite. They're going to be infinite with, in most cases, unless your tree has a very small integrate, strictly smaller than 1. So what's happening there? If all those other trees are infinite, why is this one stopped? So the picture to understand why the continuous time processors are so different from the static models, to say that is to look at a picture like this one. So at the beginning, we have the continuous time branching process that's doing all sorts of things like that, right? This is my root. What I'm doing here is I'm plotting, or I'm drawing, depicting on the same level, the members of the same family. So this would be vertex 1 and 2 in the continuous time branching process. A lot of wacko things are going to happen at the top. Like they're going to be very close. There's going to be multiple, once we collapse, there's going to be multiple edges. It's going to be very, very weird looking and highly non-tree-like. However, the number of vertices or number of nodes in the continuous time branching process that are close to the top is very small compared to the number of vertices that can be found down here on the fringe. So if you're picking uniformly at random one node from this big tree, then chances are you're going to pick somebody down here on the fringe. And once you're down here on the fringe, the picture looks very different. So this is my node on the fringe. This is the uniformly chosen vertex, let's say, that we picked. This one in this picture has a family size of 1, so it only has one edge that is connecting it to whoever it attached to. But then that guy has another offspring that had three members in that family connected to this guy over here, I. And these three, only one edge is connecting to I. The other 2 edges, these blue ones, are connecting to somewhere outside of our little tree over here in within the red triangle. Same thing here. Here's another element, another vertex that came in and decided to attach to I. So this first offspring of that family is the one that attached to I. The other one attached somewhere else. So when we collapse, there's only one edge. Same thing here. This family had a family of size 4. It's the second individual in that family that connected to this vertex over here, to this node before the collapsing. And the other 3 members of that family actually connected to the outside. So because this is a typical picture, you can see that it's still a tree. Hence that the local weak limit is a tree. And because this length of time is finite, it's a stopped tree. So the local weak limit of these dynamic models is in general going to be always a finite tree with probability 1, which is not the case in most of the static models. So this is something to keep in mind, like that there are going to be important differences between the 2 family of models that actually do go beyond this observation that I just made. Any questions so far? No? Okay. So just to give you some context, historical context of what was known, like the first time that the first people who actually gave a proof of the local weak limit were Berger, Borgs, Chase, and Saveri in 2014. And they did this for the special case where the out degree is always M, deterministic value M for all the nodes. And the way that they got the proof was using something called the Polya point graph. So Polya-Ern type of analysis. And they were able to describe that for the preferential attachment case. So the case where F is a linear function with, of the form X plus something, X plus B in the context that I gave you here. Now, there's also some other interesting results for the general case attachment function F. The tree case where everybody has exactly a degree 1 was already described in Rudolph and Valco in 2006. And the uniform attachment case where the function F doesn't depend on the current degree. So the function F is a constant. And the out degree was Brandon was describing Garavaglia and van der Hosten in 2017, although there was no weight limit there. Now, what's interesting about this graph is that it has behavior that maybe at first glance looks a little bit unexpected. So here, for the purpose of these next couple of slides, I'm going to use N to denote the degree of the root. So the in degree of the root of the tree. So this is the in degree of the typical vertex, the uniformly chosen vertex. Now the in degree in this picture is going to be the in degree of this guy, right? So in this case, the in degree is 2, right? In this particular example for the N. So once we look at this, in real networks and real world networks, the degree distribution is usually going to be a power law. That's what is observed in many interesting examples. Here, in the degree of the root of our tree, we're going to have different behaviors depending on how we choose our distributions. So I'm going to call F to be the tail distribution of the out degree. Again, remember, the only thing that we're assuming is that it has finite means. I'm going to call that finite mean mu. In the case where the attachment function is uniform, is just a constant, it does not depend on the value of the degree, what we get is that the distribution of the in degree is a Poisson random variable that is modulated by the distribution of the out degree. It's a mixed Poisson. Those of you who are familiar with the behavior of mixed Poisson random variables, you know that whenever you pick D to be heavy-tailed, then it takes over the behavior of the Poisson, of the mixed Poisson. So the tail behavior of D and the tail behavior of N are asymptotically equivalent. With the corresponding scaling if needed. And what that means is that even in the uniform attachment case, if we pick the D to be, let's say, regularly varying, despite the fact that there is no preference rule attached to the way that people are connecting to each other, we will still get a scale-free graph that is heavy tail and with a tail index that is proportional to that of the out degree. Now, when we don't have heavy tails, so the special case where the out degree is a constant, so has no tails of any kind, then the in degree distribution is actually a geometric, so that's very light-tailed, right? So you go all the way from super light-tailed to potentially scale-free and heavy-tailed, even in the case when we're not actually using any kind of preference rule. And that's sort of interesting to think about, that here it's the out degree that is modulating how, the in degree of the graph, even when we're not using preference rules to decide how we attach. Now, the general case is a lot more interesting, where F is, let's say, linear, or in general, we usually call it just a regularly varying function with some alpha that is strictly positive, so that we spend all the space from that geometric case to the heavy tail, super heavy tail linear preferential attachment model. So if F is of this form, then the in degree, according to our limit theorem, takes the form of a superposition of IID copies of the attachment function psi. Here, these are IID copies of my pure birth process. And here, the tau, they're all stopped at the same random time, which is that exponential length. Remember that random time is just the length of this tree. So this is what tau is representing, the time that it takes us to go from here to there. So now that we've stopped those, then there's a lot of dependence. Even though the xi's are IID, they are extremely dependent through the fact that they're all being stopped at the same common random time tau. And because of that, we end up with very interesting dynamics for the in degree. In particular, the in degree distribution has a tail that decays as the expected value of e to the minus the Malthusian parameter, this function g1, which is just the integral of the reciprocal of the attachment function. In the case where F is aligned, this is the harmonic series right here, so you get the logarithm. And therefore you get what we all know that the preferential attachment graph has, which is regularly varying in degree distribution. But what's interesting is that once you move away from the alpha equals to 1 case and f, make, let's say, alpha somewhere in the middle, then a lot more complex behavior pops up. And G1 goes from being a logarithm, in the case of alpha equals to 1, to being a semi-exponential function, so some Weibull type tail. And that Weibull tail parameter depends on the alpha. And it turns out that depending on how you move the alpha between 0 and all the way to its limit 1, you can span the entire family of the Weibull distribution, right? So you get all the different types of Weibull tails, which are neither exponential, but not as fat as a heavy tail. So in some ways, this family has that nice feature. This random graph model has a feature that you can model a lot of things with intermediate sort of looking in-degree distributions. The out-degree distribution is always whatever you make it, right? That's prescribed. So whatever you choose the out-degree to be, that's what you're going to get. But the in-degree is being modulated by both the attachment function and the out-degree distribution. So that's a nice little thing. So now let me make a little, spend a couple of other slides explaining how else we can think of these dynamic models as being very, very different from the static models. Now, what you pick in a real life situation to use as your model will depend on what is important to you to be able to replicate or to mimic. The static models do a great job in being able to mimic, any kind of in-degree and out-degree distribution, correlation between the in-degree and the out-degree of the same vertex. You can get the small world phenomenon. You can get many of those properties that we expect to see based on real world data. But if it's very important for you to the problem you're analyzing to think about how the graph is being generated, what are the mechanisms in which new vertices choose to adjust, you might be tempted to think like, I really want to pick a model that can explain that can explain why the graph is the way it is, rather than just a model that is mimicking what you already see. Now, if you go in that direction, there's a couple of things that I want to say about how one has to be careful about what models to choose, especially in the directed case. And one of those stories is related to the centrality measure given by the Google's PageRank algorithm. So Google's PageRank algorithm, in case you're not familiar with it, is what got Google started as a company. And then it's an algorithm that allows Google to rank all the web pages in the World Wide Web according to some universal number that it then uses to decide in which order to display the results of any search that you make. So if you do a search for UNC Chapel Hill, there's going to be a lot of websites that are associated to UNC Chapel Hill. But, depending on their importance and their page rank, they will be chosen internally. Some will be chosen to be closer to the top than others. On top of that, of course, today the search algorithms are highly personalized. So there's an extra factor that goes into how Google decides how to display results that has to do with your personal computer. And if you want to try this as an experiment, take 2 computers brand new and start doing different searches, and then they will change the order in which results are displayed in general. But just to keep everything very simple, let's stick to the original PageRank algorithm, which is nothing but a recursion or a solution to a system of equations. So here, my system of equation is given the PageRank of vertex I is given as a weighted sum, weighted by the out degrees of the inbound neighbors of that vertex. So here, the RJs are the PageRanks of the inbound neighbors of vertex I. This QI is called the teleportation parameter, and it determines where, or personalization parameter, which determines where you would restart your lazy surfer random walk in case that you're prompted to start again. So PageRank, from the point of view of this description, is just a solution to a system of linear equations. It fits into that framework that I mentioned very early during the talk, where it's a map phi, in this case a linear map, of the inbound neighbors values. The R's are these ones. And it uses information about the vertex attributes of those neighbors, which in this case are going to be the out degrees and the teleportation parameters. So it fits that. It has no noises. Once the graph is realized, there's no randomness in PageRank. But it still fits that as a trivial case of a process that is not really Markovian. That is not really a random. So this vector Q in general is, as I said, it's modulating in a personalized way. Well, how is it that PageRank will reset itself once it teleports? And this teleportation idea comes from the fact that PageRank is also depicting a random walk on the directed graph. And every once in a while, so whenever you're at any vertex, it chooses one of the outbound links to follow with equal probability among, with the same probability among the number of ones that you have, and goes there and keeps on going, or it chooses to teleport with a certain probability of a coin flip. That coin flip lands, chooses to teleport with probability 1 minus c. That's called the damping factor. So this is the probability that makes the jump happen. And when it does, it lands in vertex I according to this personalization vector Q. So one thing that was very popular, I want to say like 20 years ago when the internet started, was this idea that PageRank is measuring centrality, is measuring importance. And it had this funny behavior that people call the power law hypothesis. In other words, many of the graphs that we have, in particular the web graph, the internet graph, many social networks, or most social networks, are scale-free networks. Scale-free networks means that the in-degree follows a power law distribution. So something of the form, the proportion of vertices that have in-degree greater than x decays as a power of x. So in this case, let's say with some index alpha. Some graphs have both the in-degree and the out-degree V power law. Some of them only have the in-degree V power law. Either way, we're going to call those scale-free. What people observed back 20 years ago was that when they looked at the results of the PageRank algorithm, of that centrality measure, they would look at who are the vertices in the graph that are very highly ranked. And they would look at that distribution, this one right here. And it turned out that that distribution was also a power law. Not only was it also a power law, but it was a power law with the same index as the in-degree. This is what was dubbed as the power law hypothesis. Later, years later, we were able, Nelly Liedbeck and I and Ning Yuan Chen, one of my students, we were able to finally figure out that yes, indeed, this power law hypothesis is actually true for almost all the other models, the static models that I had shared with you earlier in the talk. So in most of those cases, indeed, we were able to prove without any issues that that power law behavior, that agreement between the two tail indices was actually observed. So we were all very happy about that. It seems that those static models do a great job in mimicking what empirically one sees in real world networks. However, this was all nice and good. At some point, Shannon and I were like, well, let's see what we can do with these sort of preferential attachment models. Like, there's something nice about being able to explain how exactly the graph is formed and not just taking that picture, that snapshot of what we already see. So we went ahead and tried to figure out what the story in that case was. And we took at the beginning, the simple case where the out degree is just a constant. So every node in this model, in the collapse model that I explained, has the same size of the family M. And we were able to actually work out the asymptotics for that PageRank distribution in these other finite local limit that is this collapse tree that I explained earlier. And we were able to prove, again, convergence to some random variable R, and we were able to describe the tail behavior of R. So the limiting PageRank distribution was, again, power law. In this case, we have two bounds, one on the top and the bottom, that coincide up to the constant. However, if you look at the indices, the tail indices for this power law, that does not in general agree with the tail index of the in-degree. So what we saw was the first counterexample of the power law hypothesis. These models do not actually follow the power law hypothesis. Interestingly enough, in the uniform attachment case, where everybody, attaches without looking at the degree of each person, and the out degree is fixed again, so the in degree is geometric, so it's light tail as light tail as it gets. However, the page rank is also power law here. So again, the page rank here is depicting something very different from what the in degree distribution does. And this actually has many consequences to how is it that vertices on the graph that you're modeling are behaving with respect to each other. And that's why this I find particularly interesting to try to understand. So these models will in general fail the power law hypothesis. Cheyenne will talk later today about another model where they can get back the power law hypothesis and explain why it's failing in this model. Now, one interpretation of what this lack of power law hypothesis tells us is that in the static graphs where the power law hypothesis holds, what we're seeing is that essentially the high page rank nodes and the high degree nodes are sort of uniformly spread throughout the graph. They're not necessarily close to each other, so they're just everywhere. The entire graph looks fairly uniform. If you took you sample the graph in a very, very large, and you take a magnifying glass at different areas of the graph, they all sort of look the same. And the large degrees are going to be sort of sprinkled throughout everywhere without too much correlation between them. However, in these dynamic models, like the preferential attachment family models that I've talked about today, that's not exactly the case. And if you look at the local neighborhoods, somebody who has a very high page rank, high centrality value, probably also has a high degree. But it's not only that that vertex has a high degree, but also all its offspring will have high degree. And again, if you go back to this picture, this actually makes quite a lot of sense. High degree, somebody to have a very high in degree here is related to how high up here it is. Obviously, if I pick somebody up there, it's older. It has more time to accrue offspring, to grow offspring, right? And therefore, it has more chances of having higher in degree than somebody down here who's younger and who doesn't have to. But if I tell you that somebody here is old, then its offspring are old too, which means the offspring also have high degree. And because page rank is a measurement, it's measuring not just the in degree of the vertex, but the in degree of the inbound neighbors, then this creates that discrepancy that we're observing. So in other words, when we look at dynamic graphs, the local neighborhoods are actually quite different than what we expect to see on static models. Now, here's an open question for those of you who are interested in doing some network analysis from a more statistical point of view. How would you argue that, that what we see in a real world network is better modeled by something that looks more like a static model or something that follows these dynamic models, for example? Like, what's nice about dynamical models is the fact that they come with a story of how the graph was formed. But if that story does not reflect what you're seeing in the data, well, then there's something to open up the doors to many more models. Now, just as I said, like, this is one thing that the two types of families are very different in the way that their local limits behave, the shape of the local limits. Here's another one. In real world networks, directed networks, usually we expect to see a giant, strongly connected component, right? That's something that people who work in this area often take for granted. This model like this one doesn't have one. So again, there's going to be issues that are coming up from the fact that this temporality that the dynamic model gives you that are lost in the process compared to things that we observe in the real world. So these are just a couple of things that I wanted to mention in case that you're ever wondering which model is best. And with that, I will open the floor to questions.